Good morning, everybody. Welcome again for this new seminar here at the Instituto de Astrofísica de Andalucía. And today we will have the talk by Dr. Álvaro Álvarez Candal, and he will talk about the new phases in the many phases in the asteroid. So Álvaro, he got the degree in astronomy by the University of Córdoba in Argentina in 2002. Then the PhD in astronomy by the National Observatory in Rio de Janeiro in Brazil in 2006. He's been postdoc at the Paris Observatory, LESIA in France, and the European Southern Observatory in Chile between 2007 and 2013. Then he moved to Brazil in 2013 with a research position where he stayed until 2019. Just before the pandemics, he moved to Spain, where he contract of Doctor Distinguido at the Alicante University on 2020. And he became a Severo Ochoa postdoc in 2021. Her career has been focused on observations of small bodies from asteroid to trans-Neptunian objects using photometric and spectroscopic techniques in the visible to near infrared. So thank you very much, Álvaro, for being here, and the floor is yours.
Thank you, Bernard. Thank you, everybody, for being here. Well, I'm Álvaro. I'm very happy to be giving this seminar. And first of all, I would like to congratulate the Institute for the new Severo Ochoa accreditation. I think that's a great news, and well, it's going to be awesome for the Institute and for the people that will cover it up. Oh. Sorry, I'm not showing my screen, so... Oh, no, I'm not sharing. This one. I think now it's showing it. Okay, good, thank you. Gracias. And so I'm going to show you the results of a few works that we've been carrying out for the last few years, since 2016 in particular. And first, now this thing doesn't work. I would like to, okay. Yeah, I would just like to show the people that's been involved in this. People from Brazil, from here, from Spain, and from a few other places. Some of them were students at the time, and some others are still students, and a few of them are not anymore in science as well. Just a short outline. I'd like to do an introduction of the topic, speaking mostly about the small bodies, just to hopefully move smoothly to what the phase curves are. So it's going to be the main topic of this talk, and then speak directly of the work that I've done with asteroids, TNOs, and coming back to asteroids as well to do some concluding remarks at the end. So, small bodies are asteroids, comets, and trans-Neptunian objects. This is a picture of basically the population of small bodies. This is just taken from the Minor Planet Center a couple of weeks ago. Don't mind the colors. This is just to show you that we have objects that move from inner Earth objects to the main belt, to the trans-Neptunian region. Here we can see mid-motion resonances, the Jupiter Trojans, mid-motion resonances as well in the trans-Neptunian region, the central population, objects that are being scattered by Neptune right now. So this is a very complex picture of different kind of objects all spread in the solar system. And any model of the solar system we want to develop must explain the thing we are looking right now. This is over 1 million objects, and it's going to keep increasing when further future surveys start to release more data, like the LSST or things like that. This is going to be a lot more crowded than it looks right now. In this talk, I'm going to include the dwarf planets as small bodies, because why not? I mean, there are just 6 or 7 small dwarf planets discovered, and this is a new definition we made up in 2006. So I'm going to just consider them as small bodies. and go on from there. As I mentioned, this distribution of orbits we see now, and this is in some major axis and eccentricity space, should be explained by any model we make of the evolution of the solar system. This is a nice picture, rather schematic, but very nice, published by Deneo and Carré in 2014, which basically shows what's the current paradigm of the evolution of the solar system. We know that the giant planets migrated in the late stages of the formation of the solar system, when there was still some gas left in the disk. The planets were migrating inwards, and migration type 2, I think it was, due to the mass. Jupiter was migrating faster than the rest of them. At some point, Saturn fell in the gap that Jupiter opened, and it caught up with Jupiter. And they got captured in a mean-motion resonance. If I remember correctly, it was the 1 to 2 mean-motion resonance. And when this happened, due to this particular configuration that Jupiter is a very massive, and it was an inner planet, the motion reversed. So it sounds crazy, but dynamically it can happen. So instead of migrating inwards in the presence of gas, they started migrating outwards. When they do this, they start a very chaotic epoch of the solar system. Something similar happened to the external planets. They migrated inward. They fell into a mean-motion resonance and started migrating outwards. This migration stops when the gas dissipates from the disk. Once the gas dissipates, we are left with the planetesimals that will form in the disk, the protoplanets, and well, the massive giant planets. Then it starts a new migration, already proposed in the 80s by Fernandez and Ip, which is called migration by planetesimals. It's just the planetesimals left, they interact gravitationally with the giant planets and interchange angular momentum, and they move. When this stage happens, the only giant planet that is able to eject objects from the solar system is Jupiter. So it's the only one that migrates inwards a little bit. Due to its big mass, it migrates just a little bit. The other 3 planets, they migrate outwards, especially Neptune and Uranus and Neptune. And when this happens, they encounter the planetesimals, which are scrambled all over the solar system. So objects that were initially in the outskirts, say trans-Neptunian objects, could be placed into inner orbits, like in the main belt, and objects from the main belt were certainly ejected from the inner solar system to the outer parts. This kind of migration is not smooth, it's grainier. So it needs to be grainier to be able to explain a few other things, like for instance, the possible presence of more than 4 giant planets, more than 4 giant planets, in particular 6 or 7, a 5th or a 6th giant ice planets, more similar than Uranus and Neptune than to Jupiter and Saturn. When this migration happens, as you see here, this is the grainier. It means giving these little jumps happen whenever one of these giant planets encounters a planetesimal. Depending on the mass of the planetesimal, the jump can be big or small. So at some point, one of these hypothetical 5th or 6th planet might have encountered a massive planetesimal that puts it into an orbit that may take it into an encounter with Jupiter. If this happens, Jupiter will kick it out. So this is supposed to happen in the solar system. And when these things happen, when this planet is ejected, where there is a massive chaos in the system, and this explains a lot of features that we see today, like the presence of some irregular satellites, the mixing of primitive asteroids in the inner belt, and the current distribution of the mean-motion resonances in the external solar system, and things like that. But again, this is hypothetical. In the end, what we want, or what I would like to understand better, it's the current distribution of minor bodies in the solar system. This is just the main belt and the Trojan region. I would like to extend this up to the outskirts, as I showed you in the first figure. And this is an unbiased picture of these letters here are the, let's say, they associate with the kind of spectra the object has. S, C, D are the most, S and C are the most common. The S let's say it's a more rocky object. The C are more primitive objects. So I'm not gonna get into this one because they are marginal populations and they don't appear very often. These are the most important in terms of numbers. I want to stress this in terms of numbers. So we see that the objects that looks more rocky, let's say, they tend to dominate in the inner parts, where the objects that look more primitive, say, they start appearing in the external parts. And but overall, there is a great mix of objects here. These taxonomical classes, which is these are they're called based on the spectra or photospectra, depends if you usually we are working more with photospectra because we have more data, so we can have better statistics. But these things are based on individual observations, so at most 2-3 observations of the same object in different places. And what's currently done is taking an average on a weighted average or some things like that. This, I will try to convince you by the end that this is not strictly correct, because there is an effect that we know that the spectrum may change its shape. It's especially if it's a slope when observing different geometrical configurations. So in principle, this is very nice and this works nicely and it's very approximate to what reality is, but there is a bias here that's not being considered, and that should be included in any taxonomical classification. And this was mentioned by Kari Muinonen in the Severo Ochoa meeting we had a few weeks ago. And it was the first time I heard someone saying it out loudly. How we study the minor bodies? Well, I'm an observer. I'm not a theoretician, I'm an observer, so I'm going to just speak about observations here. There are basically 2 ways you can do this, either from the Earth, okay, or nearby the Earth, and doing the usual using one of the usual techniques, photometry, spectroscopy, parameter, over a broad wavelength range from the ultraviolet to the infrared, and so on and so forth, or wherever you can have a window, you can observe within our atmosphere. Or you can do it in situ using spacecraft. We can go to some of these objects and actually do very nice studies there. But I'm not going to speak about spacecraft here, because I want to have a big picture. I want to look at this from far away and see big structures. Spacecraft are awesome. They provide a lot of information, very detailed information, but of a handful of objects that they can be placed into the context of a more generic picture, let's say, but they don't give this smoother thing I want to see. I want to identify structures in the large scale. I don't want to just focus on one particular object. I don't want to know a lot about one thing. I want to know a lot about a bunch of things to be able to do statistics. In particular, in this talk, I'm going to concentrate on photometric studies over a broad wavelength range, or at least as broad as possible. But before getting into the photometry, I have to speak about brightness variations, because I'm going to be studying these things, brightness variations and their sources. So we have to be able to tune these variations to understand what are they, where do they come from, or how we deal with them. The first source of variation is the rotation of the body. This is very schematic. Let's say flux is in this scale and time in this scale. This is an irregular asteroid. You can think is this about the case. Okay, and when it's rotating, it's changing. It's a reflecting area. We are seeing reflected light. So when it's the maximum area, we see the maximum flux. Then it rotates 90 degrees, and we have a minimum of area and a minimum flux, and so on and so forth, till the object completes a rotation, and we have its rotation period and its amplitude. It can be as this amplitude can be as high as 3 magnitudes in some cases, or it can be as low as almost 0 in some others. Another source of brightness variation is a change of aspect angle. The aspect angle is the angle between the line of sight and the rotation axis. The rotation axis, let's assume there is no nutation nor precession, so the rotation axis is fixed in space. So when you're observing the object here, you're going to observe one aspect angle, let's say 45 degrees. When the object moves into this position of the orbit, I'm going to have an angle of 90 degrees. So this changes how the rotation is seen. So it changes the amplitude of the light curve, and it changes the rotation, the amplitude I'm going to be seeing. So this is a source of brightness variation. No, not this button. It doesn't work. And last but not the least, phase curve. So the brightness of an object here, it changes due to the changing distances to the sun, which is emitting the light that's going to be reflected by the object, and the distance from the object to the Earth, where there is the detector, the observer. These two effects can be removed just by normalizing it, and we obtain what we call the reduced magnitude. Okay, then we are just left with one variation, that is the variation in the phase angle, which is the phase angle is basically the angular distance between the Earth and the Sun as seen from the object, and it gives us a proxy of the fraction of the surface that's illuminated and seen as seen by the Earth. And this is the things I'm interested in: how the brightness of this object changes when changes the phase angle. These are things that has been studied in the 50s. This is a seminal work by girls. I think this was Masalia, the Asteroid 20 Masalia. And he saw, and plotting this reduced magnitude, removed the effects of the distance and removed also the effect of the rotational variations. The plot, the phase curve that's plot, has this shape. It's not a linear that was supposed to be, okay, but it has a surge at low phase angles. So the phase curve is composed of this linear part, this surge, which is called the opposition effect, which is a combination of two phenomena. First, when you're getting into the opposition, you're getting into a configuration when you are the source, the observer, and the object aligned. So there is a minimum of shadows that you see in the object, as well as there is a physical effect, which is a coherent backscattering, which is two rays of light going in the same direction, but in opposite sense. They tend to interfere, producing an increase in the brightness. What's important of this curve as well is where it cuts the y-axis, which provides the absolute magnitude of the object. For a solar system or for a minor body, the absolute magnitude, it relates to its size and its albedo, which is how the light is being reflected off the surface. So this is why absolute magnitudes are important, because if we have an estimation of the albedo, we may estimate or have a decent estimation of its diameter. Its diameter is one of the key properties to know these objects, because tied with the mass, we get densities and stuff like that. From the phase curves, we have the relation between the apparent magnitude, again, normalized by the distances, and this is a function of the absolute magnitude, the phase angle, and a series of parameters that are generically called G here. And these parameters depend on the photometric model that's going to be adopted to describe these curves. The current IAU accepted model is the AG1, G2, but this works well when you have a very dense coverage of your phase curve and a very high quality of the data, which is usually not the case. So I rely on the AG1-2 asterisk AG1-2 star model by Pentile et al. In 2016, which works better in a more sparse coverage of the curves and not so high quality. And it works really well. Of course, there are other models as well. A lot of people that works either on empirical models or on physical models like Hapke or Shkuratov and things like that. Shevchenko as well. How we work with phase curves. There is a traditional way. It's I request for observing time. I select my list of targets and I observe them. I need to observe them. The phase angle depends. It's the angular distance between the Earth and the Sun as observed from the object. So I have to observe this in many different positions of the orbit of the object. So I need a lot of time to do this, unless I'm observing an object near to the Earth that changes its position very fast. If I'm going to the main belt or to the trans-Neptunian region, I need a lot of time to do these kind of curves. But the good thing of this strategy is that I can choose which objects I want to observe. I know which phase angles I'm going to observe it, and I control a lot of the observation setup, filters, extinction, etc., quality of the night, and whatever. All of this is very controlled, so I can create very nice phase curve like this one of Nisa, Belskaya, and Shevchenko. And there is a new approach, let's say new, that's become available to us thanks to the availability because of the large photometric surveys. This technique relies on serendipitous observations. So these surveys observe the sky with different techniques, with different strategies, because one of them are extragalactic, others are dedicated to cosmology, or a few of them are dedicated to small bodies, but they cover the sky. The minor bodies the small bodies happen to be there, usually as contamination. There is people working within each survey, or most of the surveys, that flag these moving objects, link them to minor bodies, and provide this as extra value catalogs that are used by the community. When you do that, they provide us with this sort of data. Here, there is no control over when the object was observed or where the object was observed. We have to work with what we have, but it can be done. And well, this is a very nice case of the Atlas survey. This was published by Nike and collaborators. The advantage of this is that it provides with a lot of objects. Because a survey that's been observing for a few years, the whole sky is going to observe a lot of asteroids in a lot of different positions, and we're going to have a lot of coverage. So that's very nice. And we're going to have many objects, a lot more than we can cover in a traditional way. Let's say traditional in a way that, meaning I go to the telescope with my target list and I observe them. The data is usually already calibrated. The problem is that the observations are taken at an unknown rotational phase. The object happens to cross the field of view and it's observed. So I don't know in which moment of you remember the sinusoidal variation. I don't know if it was maximum, a minimum, or in the middle. In principle, to do phase curve, you have to have the average, or you have to remove the effect of variations. And for most of the main services, the most important service, minor bodies are usually contamination. Although it's becoming more and more important to every survey. Most of them have working groups on working on pipelines that are going to flag and link to minor bodies and provide this. This is going to be awesome. There is also another issue I want to mention. It's not strictly related with this, but because I want to come to my main motivation. There is a known phenomenon that's known as phase reddening, this is done with a laboratory spectra of meteorites. That whenever you observe a given spectrum at different phase angles, here increasing, there is a change not only in the depth of the bands, but also in the overall slope. Let's say if you fit a linear slope here, in this case, it's becoming redder. So an object observed at different phase angles may not have the same color. You observe it at 30 degrees, it may not be exactly the same as if you observe it at a position at 0 degree. So this has to be taken into account whenever you're trying to make a compositional description of the solar system, of the population of minor bodies of the solar system. So I want you to keep in mind that current taxonomies, meaning, let's say, taxonomies spectral types, are biased because they are based mostly on snapshots. One observation at one random phase angle, I make it into, I say, this is an object, a rocky object, this is an icy object, this is primitive, this has this kind of spectrum of that one. But it may change. We know it may change at different phase angles. And we also want data at the broad wavelength range to be able, in particular, with photometry, to emulate what we do with spectroscopy. Spectroscopic surveys are a lot less massive than photometric surveys. That's the main thing here. So what we try to do, or what we did actually, we went to the Sloan Moving Object Catalog, which is a value-added catalog of the Sloan Digital Sky Survey, increased by Carrier and collaborators in 2016. From there, we extracted information of about 140,000 objects. with this criteria. There is a new catalog I want to mention by Sergeyev and Kari, where they reanalyzed all data of the Sloan, of the photometric catalog of Sloan, including data that was not included here, that was taken after the last release of the moving object catalog, providing over a million objects with the catalog magnitude. I didn't use this. I started all this before this was public, and I'm analyzing it right now. But it's going to take some time because this process, as you will see, it's not particularly fast. So basically, I'm sticking to data. I want to have at least 3 data points with errors in the magnitude less than 1, say, and cover rate in phase angle of at least 5 degrees. So I say that rotational variations are important to be considered. As I don't know, I pick one observation of one object. I don't know which rotational phase it was taken. I don't know if it's a maximum, a minimum, or in the middle. So what I did was to try to create the probability distribution of all the possible rotational states for that object. I went to the database of all light curves provided by Wagner and collaborators. Well, this is the reference, but it's updated periodically. And with an a priori estimation of the absolute magnitude in the B filter, done with just assuming the nominal errors in the magnitude, I computed the probability distribution for every object in my list for over 20,000 objects or something like that. With this with this probability of the possible rotational states of these objects, I convolve with the probability, basically with the probability distribution of the magnitude, which is basically a Gaussian with a width of sigma. I know that for the Sloan objects, the Gaussian is not a correct approach, but it's good enough. Basically, this is the picture. It's worth more than equations. Basically, the black line is the probability distribution of the rotational states. So the object may have an amplitude in the light curve between -1, -1.5, and 1.5, more probably in this region. The red curve shows the probability distribution of the magnitude. This has been just put into 0 to make it clear. And the convolution, well, it gives this thing here, which is as convolving with the Gaussian, it just tends to smooth out the probability distribution of the rotational states. To compute the phase curves, I extracted the data for each object, for each of the 5 filters of the Sloan catalog. I extracted and did a Monte Carlo simulation using the blue curve as a source. I mean, I'm extracting randomly data from the blue curve. That's what I'm doing. I'm constructing probability distributions in the space parameters that I'm using the model. The model of Pentila uses basically two parameters, H and G, and this is the probability distribution. From this probability distribution, that this is because it's a Monte Carlo, it's quantified. It's not continuous. It's discrete. That's the thing I want to say. We obtain a lot of solutions that are not physical. So the model allows unphysical solutions. We have to remove this. So the physical solutions are in red. All the gray parts are not taken into account. So there are thousands of solutions that are not physical. So we remove them. And for the sake of our work, left with the option, which one of these values is the one I'm not going to provide as my nominal? In the end, any of these solutions is a good solution. It's a possible solution. So all of them are valid. Some of them may be more probable in this region, and this it's very unlikely, but it's a real solution. It may happen. So in the end, I just choose the median of the space as my nominal, as the nominal results. All the probability distribution are stored and available for the community. And these are the solutions. This is just one object that I use as my test subject. Then, well, the name is on the top. It's 1034 T1. and this procedure gives, well, a reasonably good fit. It's good to remember that the curve doesn't follow exactly the numbers, because this is using the median of the distribution. So it doesn't, the median not necessarily is the best solution. It's just one solution, the one that separates it, the one that separates the distribution in half, basically. Okay, but as I said, any solution in the parameter space is valid, so it's left to whoever uses this to choose whichever solution they want to use. We obtain over 40,000 objects with at least one valid value, with at least one valid value of absolute magnitude in one of these filters, and 12,000 objects with all 5 magnitude value. That's good. That's a very big number. In the end, what we wanted to do, if we also wanted to see if our magnitudes were where our processing was okay, if we were doing fine. We compare with a very dense database by Veres, obtained with PanStats. We have like 8,000 objects in common, and the agreement is fairly good. Our magnitudes tend to be a little bit brighter than theirs, but overall it's pretty good. And in the end, what we wanted was to create this sort of plots. These are color diagrams using absolute colors, not colors taken at one random snapshot, at one random rotational phase. These are things are corrected by this. These are, let's say, intrinsic colors of the objects. And this one, in principle, it says something, but this one is more interesting because it looks a lot like other plots being plotted, and it separates well objects have a deep absorption band in 0.9 microns, which are René knows a lot of this, the V-type objects. And here we can see 2 clumps, one of them associated to the traditionally called S-type asteroids, and other to the C-type asteroids. We moved further, and we wanted to do, as I said, taxonomies are based on observations at random phase angles, so they are sort of biased. We wanted to do a taxonomical classification with data at 0 phase angle, and this is what we did. This has just been published about a month ago by Milagros Colasso. We stuck just to 4 different groups, because the quality of the data is still not there. With our error bars, our uncertainties are still large, so going into more detail doesn't make much sense. It's going to blur too much. With these 4, we already have what we want to see in the parameter space, and here very well separated. It was done using machine learning, see fuzzy means by Milagros. And here is the V types, and here are the C types, the S types, and the X types, and each one of them has a particular spectral behavior. These 2 have absorption features, and these 2 are more linear, changing its slopes from blue to red. We started constructing our maps. This is semi-major axis, and color G minus I, and the slope just fit aligned to the colors. We're starting to see interesting things like this G minus I. It covers the region just before the onset of the absorption feature in those objects that have the absorption. So we see that those objects that are very red appear mostly in the inner part of the solar system, while in the outer of the main belt. Well, going to the outer part of the main belt, we start to see most objects that do not have that are less red and tend to have slopes that are more close to 0. So they have to be less featured objects, let's say. There's still a lot to do here, because, for instance, we know that farther away we should start to see objects that have slopes a lot higher than this, or they should start to dominate. We don't see this because there's very little objects classified as that, and because these D types objects called they've been included into the X classification. So there is still room to work here. This is just a first step, and I hope that whenever we get more data, we can start doing this with more detail and and getting more insight into particular features. I'm going to move now a little bit out, keeping into the topic, but this is going back in time because these works were previous, were published before what I was speaking before. In this case, it's related to trans-Neptunian objects and centaurs. This was the first time we tried to include the effect of the light curve to compute the absolute magnitudes. And it was the first time as well, not that in the literature there were already work by Rabinowitz using 3 filters, but it was the first time that we had a massive database, let's say 3,000 objects, worked with using data in 2 different filters. And we use an homogeneous processing, which I think is crucial. For these objects, we can use a much simpler photometric model, just a linear assumption, because we are dealing with phase angles for TNOs seldomly larger than 2 degrees, and for centaurs, just up to 7 degrees. We are in a region where we are within the opposition effect, but in principle, the assumption of linearity worked relatively well. I'm going to come back to this a little bit later. Except for a few objects, this is a very recent work, that do have a very strong opposition effect, but it usually happens below 0.1, 0.2 degrees. And it's very difficult to observe within this range. So how valid is in the end the linear modeling? Well, we've done a simulation, assuming no errors, because if we put observational errors here, this gets a lot blurred. And in principle, for the worst case scenario, which is this one, which has a phase curve covered just by 3 points, which is my main criteria here in selecting data, we may commit errors in the determination of the absolute magnitude of up to we may underestimate the absolute magnitude by 0.4 at tops, but in general the median of the difference is below 0.2 degrees, 0.2 magnitude, sorry, and this is within our uncertainty. So in principle, the linear approach to describe this nonlinear behavior, always in a restricted phase angle regime up to 7.5 degrees, works fine if we want to determine the absolute magnitude. It's not good to speak about opposition effect, because that's a complete different phenomenon. This is physics, and I'm not entering into that. But to obtain absolute magnitudes, the linear behavior it's good enough. At that time, what we did was to use the rotational data we have of TNOs. For those that we knew, we used these values, and for those we didn't know, which were a lot as well, we computed in bins and used the median in those bins. So this was the first thing we did. We also did Monte Carlo, retrieving, but in this case, the rotational probability we assumed was just uniform. The probability distribution was uniform, didn't have those dents I showed for asteroids, and we obtained these sort of curves covering this parameter space. This is an example for Eris. We obtained more than 100 objects. We tested with this data a lot of relations that were usually put forward by the community, like the bimodality of colors for objects smaller than absolute magnitude 7, or the overall the increase of redder objects in determined regions of the outer belt. And using absolute magnitudes, we didn't see any clear relation. So the main conclusion we took from this was that whenever proposing a new relation or a correlation or a predominance or whatever, it should be done using absolute magnitudes and not the snapshots obtained at one particular phase, because it may bias your result, or it may bias your thinking towards something that may not be there. Of course, this was done only with 100 objects. Maybe if we put more of this, if we add more data here, we may start to see some relations, but especially because there is data for a lot more objects, but most of them were just once or twice at most. I wanted to compute these magnitudes. I'm using objects that have at least 3 observations. The only relation that we detected actually was my student at the time, Carmen Ayala Loera, who discovered this, was this very strong anti-correlation between absolute color and this delta beta. With beta is just the slope in the linear function. It's very strong. It happens for whenever you consider small different subsets of data, just centaurs, TNOs, in different semi-major axis beams, etc., in sizes. It happens for all of them. So in the end, we concluded that it was common for the trans-Neptunian population, as it didn't depend on diameter, no location, no temperature, no, nothing that we could think about. The only solution we came out was that it depended on the microscopical structure of the surface, especially related to the size of the particles. And that was our conclusion at the time. During the PhD examination of Carmen, one of the members of the committee asked her if this happened as well in asteroids. We said, we don't know, we didn't do this in asteroids. Actually, never, as we can observe asteroids up to 30 degrees, we never studied them as just as small phase angles. We just go all the way. So, inspired by that, we came back to asteroids with the same. We already had the database of the Sloan, and in this case, we restricted to the same range we were observing the TNOs and asteroids and centaurs, and used the same linear model, applying the same, basically the same criteria, and the same method developed by us in our 2022 paper. In this case, we had, as we already had the previous paper, we could use this data as priors to increase the quality of our measurements. In this case, we determined with our method the probability distributions of absolute magnitudes and phase coefficients, and we apply the priors directly in case of absolute magnitudes and through this way in the case of the slopes, obtaining new probability distributions for absolute magnitudes and phase coefficients. This basically, this is what we've done. The original computation give this space. The nominal value is this is the median, this is the uncertainties. The uncertainties always are considered between the 16th and the 84th percentiles, meaning comprising the 64% of the data. And after applying the priors, the absolute magnitude gets a little bit brighter, which, as I showed you before, this is good because the linear approach tends to underestimate a little bit the magnitude, and the uncertainties as well get smaller. In fact, the uncertainties get a lot better. This is the original uncertainties, and the blue are the uncertainties after applying the priors. This is in absolute magnitudes, and it's dramatic in phase coefficient, where it gets really well, really good. And these are the results of this work. These are the phase coefficient, the phase magnitude, the phase curves up to 7.5 degrees. I want to show you this particular case here in the R filter, because in our 2022 paper, we didn't compute R magnitude. So we have priors for this set of filters, but not for this one. So whenever using this one, we get just the original data. So that's why in this case it looks so widely different than in the other. So applying priors tend to homogenize a little bit the values. They don't make it all the same. That's not what I mean. It just tends to homogenize a little bit and to get it closer to using a more complex photometric model. Once we got the absolute colors, we went to see if we had anything similar than we'd seen. And in fact, we do. This is for different, this is U minus G, G minus I, R minus I, no, G minus R minus I, and I minus Z. And we detect the same kind of pattern in every pair of filters. And in particular, using HV minus HR, we recover exactly pretty much the same thing than for the TNOs we saw in 2018 and 2019. So in this case, we have in red objects that are big, over 100 kilometers or up to 2,000 kilometers in diameter. Some of them are covered in ices, different kind of ices, water, methane, whatever. Very far away in the solar system at temperatures below 50 to 40 kelvins. And here we have in black, we have asteroids that are a lot closer in the main belt, in between 2 and 3 astronomical units, warmer surface that are more covered in rock. And we have exactly the same behavior. The only solution we came out here is that closer to a position, we are actually seeing an effect of surface property, of the microscopic properties. And in this case, we propose that it may be due to the size of the scatterers that are in the surface. I'm not an expert on scatterers, on the physical scattering of the surfaces, so that would be nice if a theoretician could look into this and give more insight into what's going on. We also wanted to address, because this plot here, basically what says in lame words, is that intrinsically bluer objects tend to get redder with increasing phase angle, and intrinsically redder objects tend to get bluer with increasing phase angle. We wanted to see if this. We wanted to see this from the point of view of the photospectra. We have the photospectra. We have the collection of magnitudes for the different phase angles. So we computed the spectra for the different phase angles for each object. We could do it. We used the Akari albedo as well to renormalize, so to remove the effects of the normalization, because for those that are not familiar to the spectroscopy of the small bodies, we usually just we never calibrate them in flux. We just normalize them at a wavelength, usually the V filter or the R filter, and we compare them normalized. To remove this normalization that could be introduced in some artifacts, we use the albedos in the V filter, and with that we remove this and put them into a more, say, physical scale. And we computed for each photospectrum different phase angle, its slope, just a linear slope, and computed its change with the phase angle. And this is basically the slope of the at zero phase angle, just using the absolute colors. And we obtained exactly the same thing for our less dense database, because we have less albedos. Just it was about 100 objects. The same thing, objects that are intrinsically bluer, meaning that the slope at zero phase angle is blue, like this, basically. They tend to get redder when increasing phase angle, while objects that are intrinsically red, they tend to get bluer with phase angles, with increasing phase angle. This is valid only up to 7.5 degrees, which is the span of our database. So instead of calling it phase reddening, I think it should be called phase coloring, because we are going both ways. Although it's phase reddening is it's very well adopted in the community, and it's I don't know if it's going to be easy to change this. So to finish, just a couple of a few sentences that I want to stress here. The first one is for the first time we are doing taxonomy at zero phase angle. We are removing this bias. We have a lot of other biases, certainly, like discovery biases, because it's easier to observe brighter objects than fainter, and brighter than and bigger than smaller. Yeah, sure. We will deal with these biases later on. But at least we are removing one that's been affecting the data since the taxonomy has been presented, and it's a problem that has not been put forward until I heard Karim Monen speak about it, basically. Phase coloring, I've shown you, at least in the range between 0 and 7.5 degrees, it can go either way. A surface can get bluer or can get redder. So whenever presenting data as a snapshot, it should consider this. Depending on the phase angle, its intrinsic color may change. So this should be included. We are in the process of including other databases of other surveys, in particular increasing the wavelength coverage, like JPass or J+, or of course LSST when it comes, which is going to observe basically in the same filters as Lawrence. So it's going to be very interesting. Problem is that it's a very slow processing of the data. I think we're looking at least into this last work we've done, and with the TNOs that we're looking into the microscopic properties of the surface. And I think this is worth exploring to actually check if there is something there happening with this, and also to make me more comfortable with myself, because ever since we discovered this this anti-correlation, we've been trying to discard any sort of systematic that may happen and that may be affecting our data. In the last 5 years, that was discovered in 2018, in the last 5 years, we have not come out with anything that is affecting our data. So it looks like this is real, this is happening. So this should be studied in a way different than only observational. It should be studied in a laboratory, or theoretically, or numerically, or whatever. That's something that escapes my expertise. Just finally, all the software presented here is available, and the data all is in CDS. So feel free, if anyone's interested in this, just request me or go to the link of the papers, and you'll find it there. Thank you.
Thank you very much, Alvaro, for this nice talk. And now the talk is open for questions, please, here in the room and also in Zoom.
Thank you all for this very nice, interesting talk. But my question is the Gaia data is already providing some kind of new information, or is able to help you to get a better, better results, or even expanding the result to more objects in the future.
Gaia is very useful. In fact, Milagros and Rene have worked with the phase curve from there. The problem with Gaia is that it cannot observe below 10 degrees in the phase curve. So it's observing in. Let me put this.
10 degrees.
Yeah, I'm gonna put the curve of Massalia, which is, it's very illustrative. Massalia. Hey. So basically, Gaia is observing this part here. So it doesn't observe this part. So we have to. But that was a clever thing in the work that
Interpolation is very high.
Yeah, and interpolation is going to give you anything. So you have to complete this with ground-based observations. On the other hand, you may say, okay, you have spectroscopy as well that can help you in the multi-wavelength thing. Yeah, sure. But the spectroscopy they're providing is average over different. They just compile different, all observations of one object, and they just average it and provide it. So there's no phase correction there. So I personally wouldn't use prima facie those spectra because they're affected by phase coloring. And in an unknown way, we don't know how. It's just there, and I take it with. It will work well to see if they have an absorption band or not. But just for the sake of composition and mapping, I look into. Okay. But that's good, because otherwise it's going to kill us.
To say, but it's an average value, so afterward you can get some kind of general information about the area, but not for this kind of
exactly. This other kind of service I need for this. LST is going to be great for this.
Yeah, what do you mean with microscopic properties of the surface? Is the particle sizes or porosity or compactness or?
From my point of view, from my little understanding of this, is the size of the size distribution of the particles. I've read a lot of this. Most of it is very hard to understand and when I meet. And let me see. The thing is, this observation at different wavelengths. On a different wavelengths, you are seeing particles. The the light is interacting mostly with particles of slightly different sizes. So my bet is that whenever we're going from G to R to I, or whatever sort of filtering we're moving, we are looking always at the bigger, at the largest particles in each of the distribution. That's what I feel it's happening here. So when I'm observing a G, I'm observing the biggest of the G, then I move to R, and I'm still looking at the biggest of the G, but I'm missing some of the G because I cannot see them anymore. Say something like that. I don't know if I can make it clear.
Yeah, okay, so, we can talk.
Yeah, so I think this is going on, but
yeah.
I don't know how to prove it.
We can do it with that.
That would be great.
More questions? On Zoom, we have questions here. I have one. So when we compare the asteroid with TNOs, we compare the linear part, but it's this linear part, this slope, exactly, not the other one.
No, that one. We don't get that. So this is not linear.
Exactly.
I'm assuming a linear behavior because it's easier, and for the simulation, you get a decent value of the absolute magnitude, but not a good description of the curve. That's it.
Okay, more questions? No question here. No question in Zoom. So seeing none, thank you very much, Álvaro, again, and see you all on the next seminar on Thursday. Thank you very much.
Pueden estar.
Son seminarios, pero tengo nuestras posibilidades.
Tenemos que hablar